Hello, everyone. I'm Fernanda Viégas, and I'm going to talk to you about data visualization for AI explainability. I lead a couple of things at Google. I lead a initiative called PAIR, which stands for People+AI Research. And we do many different things. We create open source tools and platforms. Some of those are visualizations that you're going to see today in this talk. We also create educational materials, we publish, we do symposia, a number of things. We don't have much time today, so I'm going to get right into this. In our team, one of the ways we like to think about data visualization and machine learning is that data visualization is kind of a secret weapon for machine learning. And during the course of this talk today, I hope you understand why I mean that. Since it's a short talk, I'm going to highlight just 3 uses of data visualization in AI explainability specifically. The first one is going to be in the realm of education. The second one, it's using data visualization to debug. And then the third one is about scientific insight. So these are all very kind of normal uses of data visualization in general. And we're going to be seeing how we bring those to AI. The first one is called Tensorflow Playground. And these are all projects that were done in my team at Google. And the problem here was that Google had to retrain its entire workforce of engineers to start working with AI. And we realized that it was taking a long time for engineers to have an intuition of how machine learning systems worked and the different kinds of features, what it would mean to play with different features and what the outcomes were. So we decided to explore whether visualizing a small machine learning system would be helpful in educating these engineers. And therefore we created TensorFlow Playground. So now let me show you this visualization, which is the playground. All it is, it tries to show you every single feature that you use. Can you see my mouse? Yes, great. So here on the right, I have features. Sorry, on the left, I have features. On the right here, I have the output. And what I'm trying to do in this very, very simple example, I have blue dots and I have orange dots, and I want my system to be able to find the best slice to separate these blue dots from orange dots. That's all I'm going to try to do. And so I have this big play button here. And so I'm going to play this and boom, I can see that very quickly my system, I'm going to pause it now. My system was able to find kind of close to the ideal partition of this entire background. Now, this is the simplest case scenario. If I, change my data to something that's more like a chessboard, how will the same system do? I can play it again and I can see that my system is trying hard, but it's not really being able to differentiate the blue dots from the orange dots. So what I'm going to do is I'm going to add a hidden layer, and each one of these squares is a neuron in this hidden layer. And as I mouse over, you can see that I'm highlighting for you how each one of these neurons sees the world, how it partitions the world. And these are all very linear. So let's play my system again. It's not there yet. It's trying really hard, but it's not being able to partition the background in the correct way. So I'm going to add a couple more neurons, and you can see how information flows here. And again, I can highlight and see all the different ways these neurons think about the world. I'm going to play my system again, and then boom, it actually does an okay job of partitioning the space. And I can keep going, I can do this for, say, this kind of data, which is like concentric circles. So if I, play this, it does its thing of and in concentric circles. I can change the level of noise. So right now I have a lot of noise here. If I lower the noise and I play it again, I can see it's a nicer fit, right? So why does this matter? It matters because what happened at Google is that once we had this visualization internally for retraining our engineers, the speed with which people learn to understand the different kinds of features and what was happening with as the system was training, and what did it mean to have different layers, that speed went up by 10 times. So it was 10 times as fast for engineers to understand and to try to gain an intuition of these systems. And it was all because it was immediate feedback. It was all visual. You didn't have to code. You didn't have to go back to the command line. You could actually see and inspect and explore and experiment with this very, very quickly. So at this point, we use this internally at Google, and we've also open sourced. So what I'm actually showing you today is the open source version of this online. Anyone can play with this. Okay, so this is our, oh, and the other thing that was interesting to see was that the internet, folks on the web got really excited about this and started having competitions about, say like figuring out the Swiss roll was the hardest data to kind of partition, and people started creating competitions online saying things like, how can you solve this puzzle with one layer, one hidden layer? Or how can you solve this puzzle with the shortest amount of input features? So it was an interesting thing to follow. Okay, the second problem I want to talk about, and talk about how visualization was helpful here, is the problem of debugging your data set before you debug your model. And this is something that takes time for people to realize that it's very true. Usually software engineers' first instinct when something goes wrong with a machine learning model is to debug the model. It's like, what is my model doing wrong? But a lot of times the problem is not necessarily in the model, or it's not only in the model. A lot of times it's the training data that you give the model. And so, but it's a catch-22. Today, we still lack very good tools to allow you to debug your data. And so facets was my team's first foray into trying to visualize the data that you were inputting into your system so that you can better understand, so you can try to get very quickly a sense of whether or not there might be a problem with the data you're feeding your system. So let's take a look at facets. I'm going to show you a very simple example. This is CIFAR 10. It's a data set that it's kind of one of those hello world data sets of machine learning. It's nothing more than 32 by 32 images, 32 pixel by 32 pixel images in 10 classes: car, ship, deer. Here we're looking at a few images of deer. And all we're going to do is visualize this data set. So this is what our visualization looks like. And you can see right away that I am, if I start zooming in to this visualization, you can see that I'm actually showing you the pictures that you have in the data set. And I'm showing you the pictures divided by class. So you can see the 10 different classes of CIFAR. And just by doing this, I can see things like, oh, interesting, the hues are different, the colors are different. So like on airplanes and ships towards the bottom, I have a lot more blue. Makes sense, right? Because probably airplanes are taking pictures against the sky, and ships are, against the water. When we look at the animals there, birds and deer and frog, it's more earth tone. But there's another thing that just by doing this simple operation, I can already see, which is I don't have blank images. It could be that half of my data set is blank and I wouldn't know, right? So just by inspecting this visually, I can see that there doesn't seem to be any major problem with my data set. Now we're gonna, play a few tricks here. So I can also look at this, the same data, but by hue. So now I'm rearranging the same images you saw before, the images of, in this case, airplanes and cars, and I'm rearranging them by the overall hue of the image. And lo and behold, airplanes has a huge chunk of blue, so does ship. And my animals here are definitely bulging towards the earth tones of the spectrum. Another thing I can do, I can rearrange this entire thing under a confusion matrix. So what a confusion matrix is that it shows me on the columns here vertically what humans have tagged these images as. So this is the ground truth. And on the horizontal here, what the computer, what my model is saying these images are, how my model is classifying these images. Now, the good news for me is that the diagonal is by far the most well-populated set of cells, right? So this is good because this is where the computer and the humans agree. Now, the thing I really am curious about is I'm going to filter out that entire diagonal now. Now I'm going to say, I don't want to see the correct things. I only want to see the incorrect things. And so immediately now I have a confusion matrix of all the mistakes that my system is making. And I can see very clearly that I have a couple of cells that are very highly populated. And these tend to be the cells between dogs and cats. So my system is getting confused between dogs and cats. So that's useful information, right? Because I can say, oh, maybe I need more training data for dogs and cats. Maybe I need to look more specifically at these two classes. Okay, the last arrangement I want to show you is the arrangement for the softmax label. So this is one of my last layers in my network, in my system. And what I'm doing here is the more to the right an image is on this plot, the more certain my system is that that is indeed an airplane or an automobile or a bird, okay? And my system is right. So the more to the right, the more certain the system is and the more correct the system is too. On the contrary, the more to the left, the more certain my system is that those things are not cats or not birds or not airplanes. So these are this very serious mistakes my system is making. And not only is my system making these mistakes, it is very sure it is not making a mistake. So why do I keep talking about this? Because CFAR, as I said, is one of these benchmark data sets for machine learning. Everybody uses it for image classification to benchmark your system against other systems. So thousands of papers and research projects have used this. That's fine, that's great. It's a very clean data set. When I started to, when we start to zoom in, I was very curious. I was like, oh, so what are the cats that, my system is very, very certain are not cats? And I start seeing the cats here and I'm like, okay. And I start clicking on things to see what was my system thinking, So this image here, for instance, that I just clicked on is labeled by humans as cat. And I have to agree, it is a cat, but it's predicted as ship. And my system is very certain that it's a ship. So might want to look into that. But then I started looking at more of these images. And if anyone looks towards the bottom, can you spot that two images that are actually not cats that the system is correct about? So one is right here. I click on this image and the label, the human label is cat. However, I look at this and my system is like, oh no, I'm 100% sure it's a fraud. And I have to agree with the system. It is a fraud. And so this is an interesting point where just by looking at your data, you can see mistakes that have been made and that people have been working with these mistakes because it's kind of hard to get them, to find them. And so just the ability of a visualization allowing you to very quickly look at your data set and start asking questions and playing with edge cases gives you a whole other level of insight into what's going on with your system. So facets was so useful to us at Google that we decided to open source it. So this is something that is available. It's been open sourced for over a year now, and people use to look at all sorts of data sets. It's not only images that you can put here. Okay, now on to my last problem and my last use of visualization. This is the moment when we look into visualization for scientific insight. So the big question here is, how do multilingual models work? How do multilingual machine learning models work? Why am I asking this question? Because I work at Google and Google does a lot of translation. And lately, Google has started using very powerful multilingual models for translating from multiple languages into multiple languages. We're going to get there. But before, I want to walk you through a series of visualizations that will eventually land us on multilingual models. And these are visualizations. You see here an image, a screenshot of something called the embedding projector. These are visualizations of this is again, it's another open source project that we use both internally and, as I said, it's been externalized. And this is a visualization of massively high dimensional spaces. And so we use a series of projections. Let me just start showing you what the embedding projector does, so it's easier for you to see. So this is the embedding projector. And what I'm showing you here is yet another hello world example of data set in the machine learning world. And this is called MNIST. And all it is, it's a data set of handwritten digits, 0 to 9, okay? And this was done because machine learning researchers were trying to get systems to recognize human handwriting of digits, specifically for mail services that needed to try to read zip codes very, very quickly. And it's a hard challenge because not all of us have good handwriting. And so the whole point here is to be able to tell the zeros apart from the 8s, apart from the 2s, and so forth. And what we're doing here is I'm visualizing for you this high dimensional space of digits, and I'm using a nonlinear projection technique called t-SNE. I could use other ones. I could use PCA, I could use UMAP, but I'm going to stick with t-SNE for now. Now, why is it, oops, didn't mean to do that. So why is this interesting? Because I can immediately see that I do have what looks like different clouds of numbers here on this visualization. And that's good because it tells me that the system is being able to tell apart mostly the numbers. And they seem to be clustering well. Like I can see a cluster of 2s at the top there in pink. I can see a clusters of 8 in purple. I can see now the beginning of a cluster of 7s here and so forth. And yet I can also see that there are some numbers that are kind of scattered around. So it's not perfect. It's kind of, it seems to be working mostly okay, but it's definitely not perfect. Another thing that's interesting about this is that the cluster of ones, once it gets here to the front, it's coming up on the left there in red. The cluster of ones is an interesting shape in itself. I'm going to stop the visualization here, because without being told to do any of this, what the system did is that it kind of laid out all the number ones according to the inclination of the digit. So you can see at the very top, the ones are inclined to the right. And then I start coming down, they start to get more straight. And then at the very bottom, they are kind of inclined to the left. Okay, so again, the system is turning these images, these pixels, into vectors of numbers, and it's comparing these vectors, and this is how it's kind of clustering, and it's sensitive to things like what is the slant of the number. The other thing this data visualization does for us, it allows me to highlight things. So if I highlight one of the ones here, it shows to me, it highlights for me the nearest neighbors, okay? And by doing that, I can see that the nearest neighbors, all of its nearest neighbors here are ones. That's great. Now, if I highlight, say, this 7 here, which is not next to the other 7s, I can see that its nearest neighbors are kind of confusing. They're like a 4 and a 1 and another 7 and another 1. So this is a problem, right? It's my system's getting confused here. Okay, so now that we're done kind of giving you a sense of the embedding projector, I want to go back to our question about multilingual models, okay? So this was not our team. This was the Google Translate team, the research team that works with Google Translate. They were, for the first time, they were being able to input multiple languages and translate into multiple languages with high quality, which is something that was not possible before. For every pair of languages you wanted to translate, you needed to, up until that point, train a specific model. So if you wanted to do Swedish to English, that's one model. But if you wanted to do like Spanish to English, that's a different model. That's another one. For the first time, you could input a bunch of languages and get out a bunch of languages. The question in these researchers' minds were, we don't understand how the system is doing this. We don't understand if the system is keeping the languages separate. So imagine you have a system with 4 languages here, and I'm highlighting each language in a different color. The question in the minds of the researchers were, is the system doing more what you can see here on the left, where it keeps like English on one corner and Japanese on the other corner and Korean, or is the system doing more what's on the right, where it's bringing all of these languages together and it doesn't really separate them? It cares more about the semantic meaning of the strings, okay? So it doesn't care that like the word home, the string home, and the string casa are different strings. It really cares about the meaning of those two and brings those two together. So we used visualization to actually answer that question. And very quickly, what we did is we looked at translated sentences. So an example here, the stratosphere extends from 10 kilometers to 50 kilometers in altitude. In the embedding projector, that sentence would look something like this. I would highlight, connect all the dots. I'm just connecting, that's the sentence. So the question is, does the sentence and its translation, are they separate like this, or are they together in a cluster? Okay, and so the big reveal comes now, because I'm showing you a system that has 3 languages here. It has English, Japanese, and Korean. Each one of the languages is in one color, okay? And the important thing, I know this is convoluted and kind of strange, but the important thing is to ask yourselves, do I see a neighborhood of red and another neighborhood of blue and another neighborhood of yellow? Or do I see clusters of the three colors together, right? And that was the question, that was the scientific insight. We see clusters. We don't see neighborhoods of different colors. And in fact, I can come here, I can try to come here on my stratosphere. I'm going to highlight that. Oh, let me try to highlight this again. Yes. And I'm going to mouse over its nearest neighbors, and you can see that all of its nearest neighbors, regardless of the language, are in the same cluster. And this was a big aha moment, because it meant for the first time, we were seeing the first indications of a universal language, of the system actually bringing these languages together around meaning, instead of keeping the embedding spaces of these three languages separately. And this was one of the biggest reasons why the system was able to do high quality translations in multiple ways for multiple languages, okay? So, oh, and this is a system, last point I wanna make. This is a sister system that has Spanish, Portuguese, and English. So again, three languages. And I'm doing the exact same visualization, but when you look at this image here, what you can see, unlike what I was showing before, you can see a neighborhood of red. And we're like, what is happening here? All the Portuguese to Spanish is hanging out by itself here. What's going on? So we downloaded all of this, ran a statistical analysis, and found out that these translations here were poor quality. And so in other words, these were not clustering with the other languages. And this is incredibly useful, because if you want, again, debug your system, you want these clusters of languages. You don't want a language to be hanging out by itself. And so the geometry of these spaces matter. And this is one of the things that visualization can reveal to you. All right, so Pair has a number of tools. Everything I showed you today is available online. It is open source, so you can download, play with it, give us feedback, make it better. And I will stop here and see if there are any questions.
Okay, thank you very much. An excellent presentation. I have two questions, but I will only take one of them because of time. So
Okay.
one question from the audience about the facets part. This cat that was classified as a ship, is there any way to get an explanation from the neural network why this was the case?
Oh, that's a great question. Yes, there are a number of ways to get explanations. It depends on how useful they are. So one of the things that is the most traditional kind of explanation that you can get for image classification are sensitivity maps. Because you start to highlight the pixels on the image that the model cares about the most, in order to have given you whatever classification it did give you. And so there's a number of techniques that allow you to do that. It could be that there is some shape. It could be that the system is paying attention to some kind of color or background. So yeah, there's a number of techniques that you can then apply to understand what's going on.
Okay, then a final short one. For the embedding projectors, along with the highlighting, is it correct to assume that we can export or get the partition data for filtering or even enhanced labeling if need be?
Say that again. So is it correct to
assume that we can export the partition data for filtering or even enhanced labeling if need be out from the tool, I assume?
From the embedding projector?
Yeah.
I mean, you can input whatever data you want to visualize into the projector. The other thing you can do on the projector that I didn't get to show today is you can, so again, you can use whatever projection, you can put the visualization in whatever state you want, and then you can create a bookmark that is exportable. that you can share with others, and that will always get you back to that specific state that you were in. So whatever filtering you've done, whatever projection you've done, that is capturable. But obviously, if you want to share this with someone else, that person would also have to have access to whatever data you are putting into the system.
Okay, I'm afraid we have to stop now for the next presentation. So
Sounds
now we'd
good.
like to give you a big hand of applause, but you know how it is. So
thank you so much for having me.
yeah.